Hi everybody, welcome back to the Feynman technique. Today we're going to derive a general formula for Mellin-Barnes type integrals. A Mellin-Barnes type integral is basically any integral like this. So I just plugged in some convenient values for A and B just so we can see that this thing actually converges and what it converges to. That way we can, make sure that we didn't make any mistakes during our substitutions or whatever. So the where we're going to be starting already knowing this, we're going to say that the integral from 0 to infinity of 1 over x to the t plus 1 dx is equal to pi over t sine pi over t. All right, so we're going to be starting there. All right, so let's get started working on this integral. So how are we going to get this to look something like this? Well, first of all, we're going to need to do something about this x to the b, or maybe this x to the a. I think the best thing to do would try to take care of this x to the b in the denominator right there. So let's let some new variable, we'll call it y. We'll let it be equal to x to the b. All right, so that's y in terms of x. So let's find x in terms of y. Well, that's going to equal y to the 1 over b, right? So that means that dx is just 1 over b times y to the 1 over b minus 1 dy. Let's go ahead and plug that into, let's perform that substitution. All right, let's see. So our y is equal to infinity to the b, that's infinity, and y is equal to 0 to the b, that's 0. So our bounds don't change. Our x to the a, well, our x is y to the 1 over b. Raising that to the a is going to give us y to the a over b. And then the whole point was to make this equal to y. And let's see, then our dx becomes this. Yeah, you can see we have pretty well. Desmos evaluates these things numerically, and that's close enough. I think we did the substitution correctly. Okay, so let's clean this up a little bit. Let's go ahead and bring this outside like that, and then combine our exponents. Let's see. So let's get rid of this 1 over b, and we'll paste it right here. And then we'll just do a minus 1 to take care of this. All right. So this is messy. So what we're going to do is we're going to let some new constant s just be equal to this a over b plus 1 over b. All right, and then let's rewrite our integral using that. So our a over b plus 1 over b, that's just s. All right, what are we going to do now? I think what would work is we're going to let yet another variable, z, just be equal to y to the s. All right, so this means that y is equal to z to the 1 over s, right? This means that dy is equal to 1 over s times z to the 1 over s minus 1 dz. Again, our bounds of integration are not going to change because of that. Well, we're going to need to figure out what y to the s minus 1 is. So, in terms of z. So, let's paste that over here, and we'll put a minus 1 here. Well, that has the effect. We just divided that whole thing by y, so we have to do it on the other side. But we want that purely in terms of z. So we'll copy what our y is in terms of z and paste it right there. So this is just going to be, this whole term right here now is just z to the 1 minus 1 over s. Z to the 1 minus 1 over s. Okay. So this is equal to this, so we can replace it in our integral. And then y. Y is z to the 1 over s. Y is z to the 1 over s. It doesn't really seem like we're doing a whole lot here, but this is going to work out. And then now let's find our dy and paste what it is in terms of our z's and dz's. Yeah, so we got the same thing. Again, close enough. Again, Desmos evaluates these things numerically, so it's not going to give us an exact answer, but we definitely did the substitution correctly. All right, now let's clean this up. Let's bring this 1 over s outside. And then you'll notice that this and this are going to cancel. So this just becomes a 1. And now we have it in a form that we know. All right. And we're also going to change our dummy variable back to x. X. All right, there we go. So don't forget, this is equal to what we started with. This was our original I. This is equal to this. It's equal to this. All right. Well, now I told you we were going to be using this tool right here. So let's paste that in there. Now, let's see. Let's multiply both sides by 1 over SB. Okay, so now you see that this integral right here is just equal to this. So if we replace our t with a 1 over s, it will still be valid. So let's replace our t with a 1 over s. So that's 1 over s, and then 1 over s, and then 1 over s. And we'll put a parentheses in front of there. Now let's see if that's actually true. Yes, it is. Okay. So that is valid. Let's clean this side up a little bit. This s is going to cancel this s, and this pi over 1 over s is just going to be an s pi. And again, let's make sure we didn't make any mistakes. Yeah. Okay. Great. But don't forget, this is equal to this. So what we have is this being equal to this. But wait, we have A and B over here, and we have B and S over here. But don't worry, don't forget, S was just a constant that we renamed this S. So all we have to do is copy this down there and replace S with it. We'll put it in parentheses, and there we go. Okay, so this part right here is just going to simplify to A plus 1 over B. So A plus 1 over B. And I think we are done. Let's clean it up just a little bit more. We'll put that B right there on the bottom. and then paste it there. And then let's go ahead and let's plug in various values for A and B. Okay, you can see that's not going to work because it's only going to work when A and B are such that this integral converges. So we're going to make our B a lot bigger there. Now it starts converging. Let's make, yeah, you see it's matching up. It's always matching up when it does converge. Well, or it's pretty close. Again, it does it numerically. So, all right, guys, that's it. That is the universal Mellin-Barnes integral formula. I hope you enjoyed that, and we will see you next time.